Hey, hello, everybody. Before we will dive in, we wanted to learn a little bit more about you, the people. So who of you is running ECS in production? It's not so bad. Anybody running ECS not in production yet? Significantly less. And since we have so many, I don't ask who's running stuff in Docker containers. So instead, let's dive in. So my name is Ralph Mueller. I'm an online architect on For Honor, and I'm here with my co-presenter.
I'm Louis-Michel Gélina, and I'm a DevOps team lead in the game online operations team at Ubisoft Montreal. Special thanks to our teams. Ubisoft is a leading entertainment and video game company, and Montreal is the industry's largest video game studio, home to brands like Assassin's Creed, Far Cry, Rainbow Six, and of course, For Honor. For Honor was a big milestone for Ubisoft, the first closed alpha for us, and the biggest open beta for Ubisoft with over 6 million players joining. It's a third-person combat game which lets you experience the visceral thrill of melee combat. We're going to watch a quick video to give you a feel of what this game is all about.
Tribute is a 4v4 multiplayer objective game mode. As a tribute match begins, teams will race to grab the 3 offerings that are dispersed across the battlefield. Players will need to do whatever it takes to make their way back hastily to one of their team's 3 shrines with an offering in hand. Each shrine bestows a unique blessing on the whole team that is activated once an offering has been successfully claimed. Offensive buff, defensive buff, and awareness buff. Therefore, players may strategically choose which blessing to activate by placing an offering at the designated shrine. As the battle for the offerings heats up, players will fight opponents to steal or keep the offerings. Everything can change in an instant, making vigilance, speed, and communication your greatest skills. When your team successfully claims all 3 offerings, a countdown will begin, and you will fight to defend your shrines. If you can outlast, victory is yours.
Well, thankfully, we have less frame rate problems in the game than in that video. So today's talk is all about the journey of For Honor. We will quickly touch on how we define trailblazing and what trailblazing is and why we think you should try it out. We will touch on the core beliefs of For Honor and how it helped us make that game happen. We will talk about when it makes sense to beautify for your infrastructure and when it really doesn't. And we will go a little bit more into a deep end when we talk about bridges and tunnels, all those moments where you have to do something a little bit more involved. So first, the idea of trailblazing, it is in the beginning, you know where you start, and you have a rough idea of where you will end up. It might change, but you normally know. And the idea is to get there as fast as possible. For us, we had that mantra of fail fast, but succeed consistently. So it means every time you do something, it should get you closer to your goal. Once in a while, stepping forward is good. Once in a while, you hit a roadblock. In that moment, you have to fail fast, reconsider, step back, try something else. Sometimes what you try is a little bit more on the shaky side, but it gets you forward. And in the end, when you reach your goal, this is the moment where you look back and make like that trail into a highway, because you know that you can reach actually your goal. So for us, the other core beliefs we had, we already touched on fail fast and succeed consistently. Our other main goal was the ease of development. That was the same for every other game team, but we used it for our online infrastructure as well, because your developers are your first customers. So if it is painful for your developers to develop with the stack, it will be hard to operate. And in the end, your customers will also not really enjoy it. Another goal for us was automation. That means you automate everything you do frequently. don't necessarily automate things you do once, and for sure don't automate experiments unless you have the tooling in place, for sure. Another main pillar for us was the use of managed infrastructure. For us, that means not only that we use managed databases from AWS, we use ECS. It also means that everything we run follows the idea of if it's not working correctly, don't get an admin involved, terminate the instance, respin, and bring it back up. Because that process is always faster than any time you can use to ping somebody to take a look. So for us, when we started that process, our starting point or the beginning was that our team had limited cloud experience. But on the other hand, we still wanted to try something, to go into the cloud and benefit from all those elasticity and speed and all the other nice things. To give you a little bit of an idea of a timeline for us, we were at that point in early 2014. To give a bit more of a timeline, ECS was announced in November of that same year, Kubernetes in July 2015, so we were a little bit ahead of the curve. And it was a prototype, so also because we were at that time a small proof of concept project, a new IP, we knew that we had only limited support from other Ubisoft teams, and we were somewhat in direct competition to already established in-house technology. On top of that, we were a really small team. At that time, for online, we were kind of 3 people, and we were planning to build a stack and services. So you can tell it was an ambitious goal. So before we get a little bit deeper, I hand over to Louis Michel again to show where we ended up.
So this is a block diagram of what our production infrastructure looks like. I'm going to walk you through a few of the interactions. So first off, it always starts in the game clients, be it consoles or PCs. And obviously, they talk to subservices in the on-premise data center and also to some stuff in Amazon. So it usually hits the application load balancer, which will forward requests to a front-end ECS cluster, eventually to the back-end ECS cluster, where it will most probably hit the Elasticache database and provide the answer back. We see also that the back-end services have some direct connections to the on-premise data center. They exchange bits of data through there. And there are a bunch of other supporting services. I'm not going to go through all of them, but I'm going to mention CloudFront. So there's some world state, and we'll get back to that later, that is served out of S3, but we actually put CloudFront in front for scaling reasons, and also because we can control the SSL certificate when using CloudFront. In production, everything goes through the public internet, and we'll get back to that a bit later. So this is what we ended up with, but at first we had to get in shape. So as we said earlier, fail fast. So we had a complete stack built. We used the Play framework at first, which is a high-level web framework. We used Elastic Beanstalk, which is a highly managed Amazon service, and the Couchbase as a data layer. Provisioning was using a shell script. Now, it's obvious just looking at this that this will not do. You don't need to, there's no interesting code in there. It's just a big mess. So once we had this, we revisited our pillars to see how we did. So the Play framework was not a good fit to do services. It's really geared towards web services, and it didn't work well with what we needed. Elastic Beanstalk also did not work well with the needs of the framework we were using. And Couchbase, well, there was no managed offer for it in production, and running it on the dev machines was not easy, so that was not a good fit for us. But we did fail fast and succeed consistently. We were using managed infrastructure, and we did have some automation. And I'll hand it back to Ralph.
Thanks. So our prototype for us was enough to get a clear go from our production team and the group to go ahead at least and try to go into the cloud. By that time, it was 1.5 years before launch, about 1 year before we went into our open alpha. closed alpha. So for us, it was a little bit about risk management. So we didn't want to move every service onto that new stack. So we did choose at that time 2 non-mission critical ones. There was something we called player information enrichment, or short PI, which is a service which takes data coming from the player, augments it with other information we have about that player, and sends it off for further processing. And the other feature was our faction war. There is also the screenshot of how it looks in game. It is, For Honor is all about the clash between our 3 factions, so Samurai, Vikings, and the Knights, and they fight in a world, and we model the world. So it is, with each game a player plays, at the end they get warriors. They can deploy those barriers on a territory, and in regular intervals we do a check which faction deployed more of those warriors on a territory, and then this territory will be owned by that faction. So it's basically risk for those people which play board games. Our other goals was that we wanted to minimize resources for development. That meant for us also that we couldn't block development to wait for us to have all the tech up. So everything we do had to be able to run locally, the complete stack with all interactions between them. We spent some time to make it possible to share resources. So you have to think about namespacing your databases so you can cram 100 environments onto one machine. The other things for us, which was important, that our output for our build pipelines were Docker images. That means for us also, the only difference you have between UAT and prod is scale and configuration. The code itself is always the same. So to give us a little bit of an idea, so we had multiple user acceptance testing environments. I think at our highest point, we reached something about like 150 of those. So there you can see that it's important that you can cram those things together, or else you will use a lot of infrastructure before you are already live. So for us, it was the start. This is where we really started our trailblazing. So the goal was to reach a state which was shippable as fast as possible. So I don't know if other game companies use the same term for those things, a vertical slice, but it is what we had to achieve was an end-to-end working service which represents our final infrastructure. So for us, we started by provisioning what I call the macro infrastructure, so VPCs, ECS clusters, security groups, our Elasticache instances, Elasticsearch for logging. Those were defined as CloudFormation templates we had in source control, but they were applied manually. So somebody took that file from source control, uploaded it with the web, and then infrastructure was created. Not super sexy, but the fastest you can do in those moments. So we spent a little bit more time on those components which change frequently, so ECS tasks and services. They were managed for us using Python scripts, which at that point were emulating humans running AWS CLI commands, but it was the first step of automation because nobody had to go and type those things. So to see, as a first step, we revisit our pillars. So are we better than in our prototype? We were going forward, so fail-force was all good. Development was easy because everybody could run everything they needed locally, and we could also deploy it for people which didn't have to work on a service so that they can test the game. Our infrastructure was completely managed. We didn't have any kind of server we had to manually keep alive. Databases were all Amazon offerings. ECS is also completely managed, so good there. Our problems at that moment was that our macro infrastructure was manually set up, which generates in general like a certain amount of fear-driven opposition to change anything, because nobody can be sure that there was no manual step involved, so that what you had in source control diverged from what is really there. And if somebody did a manual change, it was completely untracked. So their automation is still a little bit shaky. We had our ECS task and service management in Python scripts. Worked pretty well as long as everything is good. The problem you run into, like the moment you run into a problem, you leave the golden path. Your role-play steps are less tested, so you don't know if you can actually recover from a failure deployment. So we know that we had to also work on this one. But it's actually the place where we managed to ship this, mostly. So we spent a little bit more time on from a stack which works to a stack which is operatable, because there's a certain amount of difference. So for us, it means we spent a good 6 months of time on getting monitoring and alerting in. For us, our stack was JVM-based. So if you want to operate a JVM stack, it's really important to have JMX metrics per container so that you know what is my garbage collection doing, am I running out of memory? So for this, for us, Datadog was a perfect choice because of the business model, because we had a lot of tightly cramped containers on hardware. Also, graphing is very elegant in Datadog. There's a little bit of a screenshot. You can't read it, but nice graphs. Alerting also works very well. For us, we were able to connect our normal monitoring and alerting from our Ubisoft group with Datadog. So that means that we didn't have to manage a second stack of people watching infrastructure. It could all be done by our service center. And naturally load tests to see the services we are writing, what kind of hardware do we need, how does it behave under load. This is a step which always takes longer than anybody expects. And last but not least, defining key KPIs to see what's going on in your infrastructure. For us, we relatively soon noticed that there's kind of two kinds of KPIs. Some, I always say, like, they're a little bit too late. So for example, a container death rate already means you have a problem. Same thing for error rates on ALBs. But at least you know something is wrong. They are normally easier to get. Other things for us as an early warning system is application metrics, but it takes more time to write them. And surprisingly, actually, log rates. The moment your system starts to go a little bit out of whack, it has a tendency to spew a lot more logs, so you can use this as an early warning and try to intervene before it all blows up. So, like I said, it's pretty much what we ship with, so I will hand over to Louis Michel again.
So at this point, we had our trail. Now it was time to move on to make it a highway so we could make it happen. And we're going to go through a few of the quirks, and we call them bridges and tunnels. So a few of the quirks we did. This is a bit more technical part of the presentation. So first off, ECS boot 101. So an ECS instance, it lives in a VPC, and you have auto-scaling groups that define how many instances you want in there. And in your auto-scaling groups, you have instances, and within those, you actually configure and run the ECS agent, and then they join the cluster, and they can start doing some work. Now, if anything, so when they boot, we start off by, we take vanilla ECS optimized AMIs from Amazon, and we install a few tools, namely AWS CLI and JQ. We get some instance details in the metadata, and register the instance in OpsWorks, and configure and start the ECS agent. Now, if anything of the above fails, you end up with a bad instance. So we have loops of retries and timeouts, and after 5 minutes, they auto-terminate. The hope here is that the auto-scaling group will notice that the instance is gone and will spin up a new one that will work. What would fail was the actual yum install step. So it would kick in too early, and the network wasn't ready. This doesn't happen much anymore, but still it can happen from time to time. So what we do is we actually scan clusters periodically, We look at the auto-scaling group, how many instances it wants to have, and how many are in the associated ECS cluster. If the count doesn't match, it means one instance just didn't join a cluster, and you need to intervene. Because the auto-scaling group will not provision a new one, so you can run out of instances that way. It doesn't happen much, and this is a manual intervention thing. Next up is, we said earlier, Ralph said we want we want everything to be mostly like production. Unfortunately, sometimes it doesn't make sense. In UAT, we had hundreds of ECS services in hundreds of environments, and so it's not the same as on prod where we have only a few services on a few static environments. In production, we use ALBs at the front end, but because we're in a VPN, VPC, and UAT, we have a limited IP count, and ALBs tend to be IP hungry. So we invented HA proxy Route 53 little trick that we're going to look in more details in the next slide or two. So these only support a single node serving requests, and it does involve a bit of deployment latency before everything converges. So having 600 ALBs just could not happen. So the HA proxy container running on every instance, and that's what OpsWorks does for us. It actually provisions the service containers, stuff we want on every instance. So it scans the instance for running services. Anything new that appears, it will update the Route 53 entry to direct traffic to itself and update the local HA proxy config so that the HA proxy will route the traffic to the proper container. It looks like this. Nothing really interesting here. It does the SSL offloading, and you see there's one section per running container. You can see it routes it to the container IP using classical host header routing. And Ralph is going to explain how we patch our instances.
Yeah, for us, I mean, the slide says security updates, but there is a multitude of reasons why you want to take one of your EC2 instances out of rotation and replace it with something new. For example, you want to change the AMI, you want to use a newer version of the ECS agent, security patches, different instance sizes, so all that fun you want to do, and you want to do this without impacting your users at the same time. So we started to look what can we do, and this is a little bit the moment when you realize that ECS doesn't have all those parts out of the box. So for us, we filled that hole with a selection of lambdas. So the idea is when CloudFormation triggers an update on an auto-scaling cluster, what happens is a new instance spins up, and all our instances have lifecycle hooks on them, and we also notify with an SNS message that an instance is now set to terminate. So when an instance is set to termination, it fires off this message. We invoke a Lambda function, which after gathering some information about the instance which is going to terminate, sets the ECS instance, which is bound to that EC2 machine, to draining. Draining is a state ECS has. Sadly, there is no drained state, so you can start the process of draining. And draining means there will not be any more containers scheduled on that machine, and existing containers are scheduled to move to other places if you have the room, which hopefully you do because there's a new instance there. So I mentioned there is no drained state, so for us, the only way we have to do is periodically pull that instance to see are all the containers gone. So the Lambda re-invokes itself, checks the instance again, and when all the containers are gone, we complete the lifecycle hook, which then lets that instance die, and the process starts with the next instance. So pretty much that repeats until you're done. A few things we figured out is really that in general, when there's a hole in like an offering from AWS, quite frequently you can fill it with a Lambda. It's also important that you tag your instance with some meaningful tags because it can help you like figure out what the instance is which currently is draining. Another very important thing we found out was that it makes sense to sleep your Lambda before re-invoking yourself. You will pay for the time it's just sitting around doing nothing, but it's significantly better than going into a tight loop and getting throttled. It actually happened to us at one point when we had the great idea from at the same time change the AMI, move to a bigger instance, and remove half of our instances. And CloudFormation went ahead and, as a first step, terminated half of our instances, and then couldn't reschedule all the containers. So our normal draining process didn't last 20 minutes, but was doing things for 4 hours because the API got throttled in between and everything worked once in a while. Also, that complete process for us, it came from a blog post. I posted the link on there, so if somebody wants to take a look on this one, it's where our Lambda came from. I think this one doesn't sleep, so keep that in mind when you reprogram that. And another thing we found out is that quite frequently, if you have to do a lot of calls to gather information in your Lambda, try considering collecting them once, put them into your SNS message for the next invocation so you save on making calls the next time. So I will give the clicker back.
So we mentioned CloudFormation stacks at the beginning, so that those were all manually uploaded and parameterized. And that was scary because we didn't really know what was going on at any given time. So we improved on this part by using GitLab CI jobs. So we actually have these scripts that detect the changes, and we'll push them out to CloudFormation. So we now can use familiar software development concepts like diffs and merges to make sure what the changes are. And they're not templates, they're actually complete CloudFormation stacks. So now, what this means, however, is that you need to stage your changes because you never know what CloudFormation will do to your infrastructure. So you want to be able to practice these changes in some non-critical environment as close as possible to your production one or to your target environment. And so you know how it behaves. And when you actually merge that diff in the production stack, you're pretty confident, well, completely confident it will do the right thing. The same principle also applies to what was Python code manipulating ECS tasks and services. So the same here, however, the Python code actually generates the stack from configs held in another system and generates the new desired state and pushes that to CloudFormation, and you get nice features like free rollbacks and a bunch of other cool things that CloudFormation will check for you. So I mentioned a bit earlier the difference between UAT and prod. On UAT, the on-premise endpoints are not on the public internet, so you can't just get to them. So we use there are two ways to get around that. The one we used was the VPN. So we're actually an extension of the Ubisoft IP range. So we can reach our on-prem endpoints. Some of the downsides is that the VPNs can flap and they need to be monitored. And also you don't want to push some high traffic through those because you never know what can happen. Also, we had to do a few special tricks to the host instances and containers to make them look up DNS entries to the on-premise DNS servers because these are hosted in private domains. But everything goes through the VPC, and this works for us. The alternative to this setup is to use proxies. So you just put a standard web proxy and redirect your containers to those. You do need to attach elastic IPs to those proxies and whitelist them in the corporate firewall. This is known to work in other projects, so that's a setup that can work. For production, we don't have this problem because we're just using the public endpoints on the internet. Just to complete this is the similar block diagram as the one we saw at first. You notice game clients this time are actually in the on-premise. Well, they're not in the data center, but they're like inside. And traffic goes through the VPN tunnel to the HA proxy Route 53 setup, and the rest is mostly the same. One interesting detail is we run like 100 or 150 environments on one Elasticache server in UAT, whereas in prod we have 5 or 6. So once we did all these bridges and tunnels, we looked back, and then we were happy. We felt fast. We succeeded consistently. We had our developers that were happy. They could run the whole stack, and our testers could have, each and every one of them could have their separate environment. That's how we ended up with 150 different UAT environments. We used managed infrastructure for stuff we didn't want to care about, like Elasticache and Elasticsearch, and we pretty much nailed the automation part. So now we had our nice highway. Lessons learned, everything manual is a risk. Just know about that. And then again, there's a break-even point of automation, and it changes over time. As you saw, we shipped with something somewhat fragile and somewhat manual. Still, that was the right choice at the time because we had to ship. You need to validate all the changes in non-critical but identical setups. CloudFormation can have a mind of its own. You never know what it's going to do. It can be scary to do these things, but if you can practice in a somewhat identical setup to your target environment, then you're good. When we modify some UAT environment, we actually spin up a new one and mess around and try to change because we know all UATs are pretty similar. And we actually have a staging one for production, which has all the bells and whistles and ALBs and whatnot. Service containers are hard to manage. We used OpsWorks for that. I know there are solutions now in ECS, but still it can be somewhat troublesome to make sure you have exactly one of those HA proxy containers running on each and every instance. Another good lesson learned is sometimes there are surprising gaps in the AWS offering, but Lambdas can duct tape a lot of stuff together, and it generally really works well. We didn't cover it very much in detail, but we actually have a similar setup to what we had for CloudFormations, where we manage Lambdas in a CI/CD manner with scripts, because otherwise you end up with a bunch of Lambdas with hooks and configs, and you don't know which ones pertain to what, and it can get messy. So again, CloudFormation is your friend. Tooling, CI/CD principles will help you. And of course, use managed services. You don't want to deal with Elasticsearch or Elasticache or all those other things. So leverage what AWS has to give you. Hopefully, you guys have a few questions.